Alex Freundlich. He's a professor at the University of Houston. He knows his business better than I do. So there you go, Alex.
The topic of this presentation is going to be how we can turn the moon into a solar photovoltaic paradise. And purposefully, I'm going to start with a very strange introduction. But first, I would like to acknowledge my colleagues, Alex Ignatieff, that most of you know. He's the kind of the person with whom we had pioneered together some 10, 12 years ago this idea about making solar cells on the moon. A number of collaborators from the private sector, Lance Williams, Andy Alemu, and Carlos Camajo. Takashi Nakamura from physical sciences. Oops, this one went too fast. Laurent Sibyl from BAE System, and Pete Curry from NASA Marshall Space Flight Center. And if we can go to the next slide, next please. This was a slide we used actually 12 years ago, or 11 years ago, when we, the first time I gave a talk on this topic. It happened that I grew up in France, and I was reading Tintin, and he was my hero. And Tintin is actually the first guy that walked on the moon. And that was about probably about 15 years before the actual man landing. By opposition to Jules Verne, as you know, Jules Verne, which sent a satellite, but he never sent something that landed on the moon. Actually, it wasn't Jules Verne. It was a bunch of guys after the Secession War. They had a gun club, and they want to find a way to shoot things with the gun. And they shoot that from actually Tampa, in the book. Nevertheless, the first presentation we gave on this topic, next please. It was called Destination on the Moon, and it was lunar regulated thin film vacuum evaporation and properties. And at the time, actually, I remember I had to start with almost 5 minutes of justification while we were working on something that was related to the moon. Today, thankfully, we don't have to go through those kind of justification. If we go to the next one, actually, Hergé was a very intelligent man. Unfortunately, he's no longer with us. He had figured out pretty much 20 years ago what would be the fun stuff that we'll find on the moon, like the lack of gravity, probably some interesting aspects for radio astronomy. One of the things he didn't look into, next please, was the concept of living off the land, the concept of in-situ resource utilization that the previous speaker, really gave us all the different aspects that one should consider if you're planning to go and live outside this planet. Now, one of the key parameters once you're going into living off the land is the survival. The first key to survival is energy. Without energy, probably, you will, in space operations, you will have difficulties surviving anywhere. And next. And although the initial work on in-situ resource utilization was essentially focused on oxygen, as long as the moon is concerned, there were some materials that were coming out of the processing of silicate rocks or nanotides, etc., different rocks, which were actually silicon and various metals that could be used to some benefit. Next. And one of the things is that actually, these metals, silicon, iron, titanium oxide, or titanium that you can get out of it, calcium, which is actually a very good conductor, or almost as good a conductor as copper. I think half as good. Aluminum are materials that can be used for fabrication of electronic devices. On the other hand, the moon has also another attribute, which was considered first as a hindrance and impediment. No, it's not an hindrance. It has a vacuum that during the daytime stays at 10 minus 10 torque. That's better than what we can achieve in our vacuum chambers on Earth. Especially with the semi-infinite pumping speed. The whole space is pumping. So essentially, there were the two basic ingredients here to use the vacuum of the moon and the materials to fabricate thin film solar cells. Next. And we came up with some simple idea that the combination of this vacuum deposition, thin film solar cell, and use of lunar local resources could be achieved. Next, I'm sorry. And this was the first cartoon we drew, actually, trying, to make it with PowerPoint. It was 10 years ago, we weren't very skilled. And we're getting better now. And I kept actually, even the center name was different name right now. It's the Center for Advanced Materials. It used to be the Space Vacuum Epitaxy Center. And the idea was essentially that if we have a solar-powered rover that will use electric motion to move and rove on the moon, and solar thermal energy to evaporate or heat materials, one can lay out solar cells directly onto that very fine regolith. And then remotely control that operation and have essentially solar cells made without, directly on site. Next. So, during this talk, some of you have heard already about this talk, so I'm going to go to some of the key aspects and also some of the recent advances that we have had in this field. So essentially, I will go through the fabrication. This is a cartoon of what is a solar cell. Essentially, it's two semiconductor layers of different conductivity. We're calling them p-type and n-type for referring to electrons and holes, which are the absence of the electrons in those materials. Very thin layers if they are in a configuration of a thin film. And there are then electrodes at the bottom and at the front, a layer that's called anti-reflect. So essentially, most of the semiconductors are very reflective. They have a reflective surface. One will use an anti-reflect to harvest better the light. And then there is a very big guy, and actually it's really not at the dimension. A substrate in most thin film solar cells represent pretty much 99% of the weight of the solar cell. In most solar cell systems, the ones that you're seeing on the space station, etc., in addition to that substrate, electronic substrate, there is also probably a honeycomb structure that is holding that. So the first big parameter, if weight is an issue, is to solve this substrate. So we'll go next. Now, of course, the solar cell by himself is a device that we cannot use in the mode that we are utilizing electricity. A typical solar cell will have an output voltage that will be in the vicinity of 0.5 to 1 volt. So we cannot run hundreds and, if we need 100 watts, let's say, which is not a big deal, we'll have to run probably 100 to 200 amps through that solar cell, and there will be need for very, very big wires to do something like that. So essentially the way, very soon when we started, to think about that, somebody said, rover that turns the moon surface into a solar panel. That was New Scientist a few years ago. And actually to make solar cell panel, we need to integrate a number of different solar cells together. Next. And to do something like that, essentially we need to have a support structure, in this case, that is insulating or semi-insulating, and then we need to have also insulating layers that we can deposit, and we'll get to the cartoon of how this can happen with one rover. So we can deposit, and essentially at a much larger scale, here the scale being probably about 20 centimeter, at a much larger scale, this is exactly what we are doing when we are making integrated circuits in silicon. We are making very miniature, different diodes, we're putting them together. So therefore, there is the necessity to have a material that will act also as an insulator. Next. So we'll go now first through this insulating material. And actually that was the topic of the talk that was there 8, 9, 10, 12 years ago, whatever it was. Essentially, we improved slightly upon that. If we go, the insulating and the anti-reflective coating end up being the same. Next. And essentially, we took JSC1, which is a simulant of the lunar regolith, and we evaporated JSC1. Through that evaporation process, JSC1 was very close to an anomite, gives you a mixture of aluminum and silicon oxide. Relatively high resistivity, very high transmission, so essentially it's not going to shadow your solar cell if if you're using it on the top. And also an index of refraction, as expected, that's very close actually to the mixture of silicon oxide and aluminum oxide. Next. The next big parameter, and we spend lots of time on this one, is the substrate. So what we thought it was to, if we can melt directly the surface regolith, that will provide us a sufficiently thick structure that could support the solar cell. Of course, I mean, if somebody's working on it, it's going to probably break, but I mean, it was one way of alleviating the problems of this very massive heavy substrate. Next. So here, I mean, it's how we simulate that in the laboratory. Essentially, we are running a small, this is done with an electrical heater that goes over a little boat, and we're simulating, I mean, something that will heat the surface of the moon. Next. And here, actually, some graphs are taken during the process inside the chamber where this thing is happening. And here we're showing the process of melting of the regolith. As you can notice, I mean, as a function of the power that's supplied, I mean, actually, this one is not the same one than there. Here, now we're working at larger sizes, so this is like 2 by 4 centimeters or something like that. And this one used to be a little bit tiny. That's where we go. So essentially, I mean, we need roughly somewhere about 50 watts of power per square centimeter to melt this regolith appropriately. We can stop the melt process early, but if it's stopped early, the product of the melt looks relatively, I mean, uneven. And actually, I mean, there's a good indicator here. You can see suddenly the temperature is starting to rise. That's a very good indication of a very strong change in the surface emissivity. And that's where you have now, I mean, actually, you're getting to your absolute smoothness. Next, another parameter that was quite important, actually, I mean, it's, my daughter was laughing when I was telling her about that, because, I mean, this is something she used to do when she was a kid with the sand, is the sifting. The lunar regolith, I mean, comes in, I mean, that's, it has small and big rocks. And we find out that sifting through a mesh of about 25 micron was giving us a sufficiently good quality byproduct after that, after the melting process. So here, if we go from, this is actually, I mean, we haven't melted very well, but it's unsifted. You can see a very hazy, rough surface on the microscope. The unsifted regolith at the optimal temperature, you can see many defects. Whereas here, actually, we're looking for defects to be able to focus the image. If we go next. And the composition of what is obtained of this glass, once again, I mean, it's essentially mainly aluminum silicate with some content of calcium and a small amount of iron. However, I mean, the resistivity of this glass, again, was found to be, actually, we couldn't measure it. It was so high, and it was in high megahertz. Next. Now, to show you, I mean, how smooth is this glass, this is a big picture that's, I mean, it's a picture that is generated through an atomic force microscopy scan. So what we have done, we have scanned an area, I mean, here it's about a micron by a micron, and we're looking for defects. Now, things are not at scale. Here we have 12 nanometer. So essentially, I mean, the RMS roughness that we're finding was between 1 to 5 nanometer on the areas that we checked. There are occasionally very big intrusions, because sometimes a rock of 10 micron passes through. But I mean, it's, so essentially it gives you a relatively smooth surface with a very high resistivity. Next. So the first thing that a crystal grower like myself or Alex Ignatieff will do, once you have a substrate, you want to put something on top of it. And we tried immediately, I mean, making some comparative study with commercially available glass, the regolith glass we made. And this is actually a single crystal substrate on which we deposited cadmium sulfide. Now, this is it's called the photoluminescence. It's the response of the material to light excitation. Here is the region of what's called excitons, which is some kind of label of quality of a material. You can see that actually the lunar regolith is acting not as good as a single crystalline substrate, but it's acting actually better. I'm not going to say who was the vendor, but it's better than a commercially one, commercial glass that we can buy. Next. And of course, I mean, then we experienced our first deception because we tried very quickly to make a quickly dirty solar cell. Nevertheless, I mean, it was the first solar cell made on something that is a simulant of the lunar regolith. So essentially, one can measure an efficiency here. It will be 0.9% efficient cell. So probably, I mean, it will die into the interconnect. Nevertheless, I mean, it was light responsive, and this was a cat sulfide, which is not matched spectrally to the spectrum of the sun. Next. We also tried, and we just started that, I mean, to making the silicon diodes. Now, of course, for the silicon diodes, we have two issues, and I will get back to that. One of the issues is the grain size, because if the grain size is very small, essentially you may get something close to amorphous, and amorphous silicon is not going to give you any light response unless you hydrogenate it. And hydrogenation is not, you're not considering right now something readily available on demand. So we will, I mean, it's possible that there will be lots of water on the South Pole and that will solve the problem. But right now we're assuming it's not there. The second issue was an issue about doping, but we have pretty much solved that one. We are right now sitting at a doping level which is about 10 parts per million. Here it was about probably 100 parts per million. Next. Okay, so how about the rest of the solar cell? One has a substrate. Now one has some insulating layer you can use to interconnect. But there are other things left. There's silicon left. There is some metal contact, etc. Next. So we're going now to look at the solar cell materials. I'm sorry. I'm just in bad habit of presenting while I'm pushing on something. Next. Okay. There were different processes that were used for the extraction of the silicon. Because again, if one goes completely ISRD, in the first step, I will show you that it's actually it's going to be even economically viable to bypass the existing solar cells that you're buying on the Earth to go to the moon, just based on the cost of launch. And if you go beyond a certain point, beyond a certain number of kilowatts, it makes sense to fabricate on site. Nevertheless, if you want to fabricate lots of them, you will need to extract all the materials from the rocks. And in this case, I mean, there were some studies done. For example, Rudy Keller looked at it with electrolysis and solidification of hyper-eutectic silicon aluminum alloys. And we looked, I mean, at different ways that we could, using E-beam, I mean, which is of course a very energy intensive, do a further purification of that silicon. Next. And the purities that we're able to, oh, actually that's the wrong one. Okay, it's now about 10 parts per million. Essentially, we're getting about 10 parts per million, starting from silicon that's purified to about 250 parts per million with the standard chemical process, electrolysis process. And next, so besides that vacuum purification of the silicon, next. There's animated sometimes. And now actually we're working, this is actually a graph that's coming from Don Sadoway and Laurent Stivel. And what they're doing, and that's we think, I mean, it's a very attractive approach for this study, is to, they're looking into electrolytic reduction of molten metal oxides. So essentially, I mean, different products, they will float, and you can pull out of that the iron, the silicon, the titanium, based on the weights that are there. Not being a specialist, I'm not going to talk too much about that. Nevertheless, this shows you what a typical terrestrial solar cell is made of, the different layers, and what are used here for this type of cell. So glass or silicon substrate is replaced by lunar melted glass. Silicon is still there. For the back context, we assume that there will be lots of aluminum. Silver is not much of silver on the moon. Actually, there's not much even on Earth. And probably it will be one of the roadblocks for the silicon technology. I mean, down the road, I mean, if we have to go for terawatts of energy generated with solar cells. Nevertheless, I mean, we can use titanium silicide, I believe. I mean, it's something that is not going to be as good, but could operate. And then titanium oxide is used on Earth. We could use both titanium oxide or aluminum regolith. Boron can be replaced by aluminum, etc. Next. Now, actually, I mean, once you go on the moon, you are in a different environment. So there's going to be lots of radiation. And the solar cells, I mean, that we have right now, the worst they see, I mean, is the lower orbit. Maybe, I mean, a little bit more they go, I mean, into geostationary orbit. The amount of radiation, next, is generally proportional to the number of sunspots, for those that are not familiar with radiation effects. So essentially, I mean, the small explosions that we see on the sun are generating a large flux of protons and electrons that are coming. Now, if you look at where the first original missions are planned, we're going to be very close to the beginning of a very bad cycle. And very recently, actually, in Science, I mean, or I guess it was in Science, it was there was a paper saying that this cycle is going to be probably very comparable to this one or even worse. So with that in mind, next, this is the data that I extracted from the Lunar Reconnaissance Orbiter analysis, and shows the dispersion of the proton spectrum as a function of, I mean, what's the fluence of particles and what is the proton energies. Now with that, I mean, it's, next. I will not show you any kind of, this will be the only kind of equation that you will see, but it will be a mixture of Latin and Greek. That will be the toughest we'll go. So if we're taking, I mean, the proton spectrum, we're integrating that into a silicon solar cell, and we're starting here with a very high-end cell. This is not what is right now on the space station. I mean, these are high-end cells that are giving like 18% beginning of life efficiency. If we take that cell and we calculate what's going to happen as a function of the number of years of operation on the moon, you can see that in 10 years, 18 has become 3.6. So the very high-quality cell is going to degrade very fast. There's a way to defray, I mean, this loss, and that's to use a very thick cover glass. And of course, which is going to add to the weight that you have to launch. The reason for that to happen is that essentially carriers in the cell, once they are generated, they have to travel a certain distance. And that distance, I mean, is called the diffusion length. So this diffusion length is directly proportional. I mean, you can find it in the radiation handbook of JPL or any place. It's directly proportional to the fluence of particles. Next. Now, of course, I mean, on the moon, I mean, our samples are going to be polycrystalline at best because we're going to fabricate them at relatively low temperature from relatively many poor materials. And similarly to the radiation effect, if the grain size becomes smaller, what will happen? Also, the diffusion length will go down. But one technique that one can use is to reduce the device thickness. So the device thickness, of course, I mean, you're losing some of your efficiency, but by the same token, you're also, I mean, you're not absorbing as much, but you're not losing the collected electrons. And here is as a function of the grain size, I have plotted, I mean, the efficiencies that one will get into a silicon. And these are kind of practical efficiencies. We'll see that in a minute. Next. Now, if I add the radiation into the system, what I will find that although the silicon degrades, I mean, the diffusion length in silicon degrades very fast if it's of high quality single crystal, as we are going to a poorer quality material, essentially the degradation is driven by the grain size itself. So if I can design, now the holy grail is then to design a cell that is matched to the grain size. Next. And if we do that, now it's the same graph that we had for silicon earlier. There's no cover glass here. And these are for some peaks. Actually, I mean, this one wasn't intentional because it was the peak where it worked very nicely. You can essentially get a completely flat response solar cell that could operate for 10 years on the moon. Because, I mean, it's very thin, so the degradation that it will get, it will be negligible from the radiation, and it's designed to be thin. Next. Now, of course, I mean, I'm sorry, if you can come back 1 second. That cell, was calculated to be 11%. Next is an experimental result.
Plus, I was going to say, if it's a thinner cell, then I would think it would use less material to manufacture.
Absolutely. For us, the process goes faster. If we have 2 micron, it's going to take us 1 hour. If we have 5 micron, it's 2.5 hours. So the production rate goes up. So this is actually an experimental result from Kaneka in Japan, and that shows that 10% efficient cell. This is actually not space 10%. It's terrestrial 10%, which is like probably 8.5% or something like that. Nevertheless, strangely, it's 2 micron thick. I don't know what's the grain size in that, but it's shouldn't be that far from 1 micron. Next. So our goal is essentially to improve the efficiency, and that's what we are working right now on. The early on cell we made, they were almost amorphous, very close to here. We're not getting close to the micron, and what we're using is thermal annealing post the process, and I will show you how it can be done directly on the rover. And essentially, the beginning of life efficiency is the red one here, and green is the end of life efficiency that you will get after 10 years operation. One can push that end of life efficiency to about 10%. Next. How we are doing on time?
Well, you probably have 5 minutes, Alex.
Okay, then let's accelerate, and we'll go directly to the rover. Next. Next. Okay, so now we're going to look at, from a system standpoint, what should be done to be able to fabricate these devices. So this is another drawing. Actually, this one came from Pat Rawling, who's a much better drawer than we are, Alex and I. And essentially, it shows the rover, a very early version of that rover, making this solar cell in its vane. Next. So this is actually a little bit more sophisticated image. Essentially, the rover is composed of solar concentrators. It has solar cells that are integrated with the concentrator system, a fiber optic system that brings the sunlight in a concentrated manner in the operation area, and then melters and different evaporators. Next. So for the concentrator part, essentially we're using a parabolic dish concentrators. This very concentrator was developed for space application with Nakamura, but it's used in Israel for unfilled surgeries. And actually, there was an image that I took from the author here, which shows he's cutting a frozen chicken with that. Next. So in our case, actually, essentially, we are going to point these concentrators to toward the sun. I think maybe we skipped one, if I'm not mistaken. No? Okay. Sorry. Okay, and what then the sunlight comes to this fiber optics, and to get the 50 watts per square centimeter, actually here we can get much more than that with this little design if it's at scale. We are using an intermediate refractory metal plate to heat the regolith, like in our experiment, except the heat is not coming through electricity, but it's coming in this case through heat, through concentrated sunlight. Sorry. And essentially, these things are about 7 centimeters in size, and there's a whole bundle of them. Now, to control the temperature was critical. That's just to prevent the roller of heating. Next. Okay, this is, it shows the back. We have removed, so there's, essentially, we can shadow some of this fiber optics. And I will show you how we can do that. The simplest way would be actually to use the solar cells that we're going to use for the electric motion to be articulated. So essentially, we will close or open the number of concentrators we are using. So that will be a nice and compact way of putting it together. And that by the same token, of course, it adds mechanical fragility to the system. Next. And for the evaporation, we have to evaporate downwards. Actually, we have a small prototype right now that we're trying to fabricate in the lab. Essentially, it will be a contained element in which, again, we're going to be using the fiber optic concentrators to evaporate the material and to thermal evaporate downwards. Next. And now the next issue, I mean, the way the rover is going to operate, it's going to be a continuous layout of the solar cell. Here is a cartoon, and next. The cartoon shows actually that through different evaporation, through different masks that are in front of each evaporator, essentially we are in the process of doing melting the regolith. At the same time, right after that, we have the metal bars that are going on. At the same time, then we have different layers evaporated through the mask. So in 5 steps, we are integrating a complete solar cell with its next neighbor. And then we can turn the mask 90 degrees if we are deciding if we want to make a series or parallel connection. And there's actually a version of that where we can put even a bypass diode on a certain number of making the diode backwards.
Would you make one complete cell before moving the rover to make the next cell? So you do all of the layers, all of the interconnections, and then just,
Yep.
or it would be a continuous motion?
It's a continuous motion.
Oh, wow.
Actually, I mean, otherwise, I mean, you're dividing your time by a factor of 5 steps. It's continuous motion, but I mean, it's not continuous evaporation all the time for all of them. So, because I mean, layer thicknesses are not the same, and growth rates are not, deposition rates are not going to be the same. Now, the nice part of what I mean, it's about having it continuous like that is that really you gain on time. You gain a lot on time. Also, another advantage, I mean, I didn't mention that I have the graphs. The regolith, after it has been melted, in our process, the way we're fabricating it, it takes us 30 seconds to bring it to 200 degrees C. And after that, it's sitting at about 100 degrees C, probably for another 5-10 minutes. So this whole process is going to, I mean, we have a control over the temperature of this process. So it's not that we have to make a very high temperature, I mean, evaporate on something very hot.
Well, my concern here was that as this thing is driving along, we know with the Mars rovers that they encounter various levels of slip. And so you cannot be assured of a very stable forward velocity. That velocity may change.
Oh, no, but I mean, you don't have to, if you cannot move the rover, you move the plate. The plate on which these things are sitting. You go, you stop your rover. Actually, you don't want to move. If not, I mean, you don't have a control. I mean, even a small rock, I mean, will make you miss everything.
Right.
Once you're in place, then you have your plate going back and forth. And then you go a little bit further. And actually, it has probably to be maybe even 2 rovers because you will have to plow at the same time and sift. And it's not the same thrust for slow motion and control. Next. And with that said, I mean, a rover like that, I mean, with about 1 square meter per hour capacity, should be capable probably fabricating of about 200 kilowatt per year of sunlight capacity, and which will require about not even 100, probably 50 kilograms if we're going for 2 micron thick, 50 kilograms of material. So in the first stage, if our goal is 200 kilowatt, we might as well send that with this rover. If that's not the goal, next. Oops. And of course, I mean, as you saw, I mean, there will be some radiation damage, but I mean, we can probably circumvent that by appropriate design. Next. I'm sorry, I put some animation. I should have. And of course, I mean, if you're going for something much larger, if your goal is megawatts and beyond, then it will make sense to have the same processing. Actually, it will be probably the same processing machine that gives you oxygen. That's going to also deliver small amounts of metals and operate it to a level that can deliver some small amount of metals and small amounts of connector material and so on. So I mean, and this part of it, I mean, it's actually much less of my work. I mean, it's more Alex and Mike do for the ones I mean, crunching numbers and looking into details of that. If you can just add the numbers of your rovers, and based on 4 to 8% efficiency, you can probably reach the level of some 5 gigawatt with some 1,000 rovers right now. Now, I mean, if you consider the weight that you're transporting, even at a level of 400 kilowatt, 200 to 400 kilowatt, you're ending up at 1.5 to 2 kilowatt per kilogram. Frankly, I don't know any solar cell technology that, including its support structure, I mean, I know there's solar cells on the road that they get about that range, but without connectors, without being assembled. So, so typically already at 200 or 400 kilowatt, it becomes attractive weight-wise. And then as we are going, I mean, more material is fabricated, and essentially you can get to regions where probably it will be impossible to reach, about 25 kilowatt per kilogram transported to the moon. Next. So
We
this is the
have
last
15 minutes to lunch or dinner.
Okay, so that will be the last one then. So essentially, preliminary cost projections that were done by based on the fact that it will cost about $20,000 to send a kilogram to the moon suggest that, I mean, if we take the mass of the rover, the production facilities that are needed on the blueprint of the production facilities for silicon production on the moon directly from lunar regolith, and the PV material brought from Earth, we can see that pretty much, I mean, at all levels, I mean, the cost even is starting to be very comparable to just the launch cost of the solar cells. At this level, at the level of about a megawatt, I mean, even if you have the solar cells for free, it's going to make more sense, assuming 5% efficiency. And again, I mean, I don't see why we shouldn't be able to get to 10 or 8 or 9. But I mean, assuming 5% efficiency, cost will be very comparable. And then, of course, if you're going to the gigawatt, which will make it the solar photovoltaic paradise, then you can really, I mean, get your energy for not as cheap as you can buy it on Earth, but very close. Thank you very much for your attention.